Assignment 1 of Building Structures and Materials provided an introduction to steel portal-framed construction, specifically shed construction. This assignment required a practical understanding of the process that a structural engineer might follow to calculate the loads that a portal-framed shed must withstand and the process used to design the shed, including the selection of steel members, bracing, and connections. A visit to a commercial portal frame structure provided an opportunity to make observations of the design and construction theory in practice. Further, a computer-assisted design software, SpaceGas, was used to calculate the purlin design for comparison with hand calculations. Loads or actions are the forces imposed upon a structure. Loads must be known so that the structure can be designed to withstand and perform while subjected to these loads. Loads or actions can be broadly categorized into dead loads or permanent actions and live loads, variable or imposed actions. Dead loads are essentially constant permanent actions and remain for the life of the structure. They are made up of self-weight of the elements of the structure. Dead loads are generally represented as pressure acting on a structure. For the purpose of the shed designed as part of this report, dead loads were considered as uniformly distributed loads. As part of Assignment 1, it was necessary to determine the loads imposed by individual structural elements. For example, to determine the purlin load, a purlin was selected from the manufacturer's catalogue, in this case Lysart. A weight in kilograms per metre is provided for the member, which can be converted to force in kPa by dividing the kilogram weight by 1,000 and multiplying that figure by 9.8 to account for gravity. The outcome is then divided by the spacing of the member and provides a measurement in kilonewtons per square metre or kilopascals. A review of the textbook Understanding Structures by Derek Sayward shows that where manufacturer's specification for the unit member is not available, the volume of the member can be calculated and multiplied by standard unit weights. As the dead load was not known at the time of selecting structural members, the assignment activity required a member to be chosen, its dead weight added to the calculation, and a determination made as to its adequacy. This led to members being both increased in size after load calculations were applied, and it was determined that the member was undersized, as well as members being reduced in size where it was determined a lesser member could perform. Structures must be designed to withstand live loads, such as wind loads, and imposed loads such as furniture, vehicles, equipment, and people. Assignment 1 required the use of loading codes Australian Standard 1170 to determine the live loads to be considered for elements of this example structure. In calculating these loads, the engineer needs to consider a downward pressure load on the structure, as well as a suction caused by wind. Australian Standard 1170.0 provides load calculations for checking the strength of the structure. These combinations add acted, dead, live, and wind loads together. The engineer can then determine the load with the highest value, called the critical load, and design to cater for this load. Load combinations build a factor of safety into the structural design and are designed to cater for infrequent additional loads, such as unusually strong winds or increased live load, such as people walking on the roof of a structure. In design of the domestic shed, it was important to consider all relevant load combinations prior to selecting the structural member. Assignment 1 required modelling of elements of the domestic shed design in CAD software SpaceGas. In modelling the purlin design using SpaceGas, it was determined that the purlin selection that appeared adequate using hand calculations failed the analysis of the SpaceGas software. The purlin failed by 9% when the load combination 0.9 dead load plus wind suction was applied. This may be due to different calculations being used by LISART or user error when inputting the data into SpaceGas. It was determined that the SpaceGas software is a powerful design tool for engineers when designing portal frame structures and negates the need for hand calculations in most cases. In designing the domestic shed and undertaking a basic inspection of an industrial building, it was identified that regardless of use or size, portal frame shed construction follows the same principles. Whereas traditional framed construction will generally use a beam or lintel between columns, supporting numerous rafters, portal framed construction connects the rafters and columns together with a pinned joint. Columns and rafters are usually braced by collar ties and knee braces, with purlins and girts providing stability. The portal frames evolved from historical arch construction, as was used for cathedrals and bridges for centuries. The benefit of portal framed construction is the self-supporting construction is capable of large internal voids, providing maximum usable space.